Hello, we are Ceres from the Universidad de los Andes, Colombia, and today we are going to present to you our 2026 generation rover, Chipiro. This year, Ceres was formed by a completely new team. By introducing entirely new disciplines, we allowed each area to contribute its unique expertise. This rover represents a comprehensive redesign driven by validation, testing, and system-level optimization. Chipiro's mobility and arm actuation retain our validated in-house brushless DC motors, as extensive testing confirmed optimal performance and reliability. This cycle focuses on improved mechanical integration with the new chassis and arm geometry. Critical reduction components are being upgraded from PETG to precision machine aluminum, increasing stiffness and durability while preserving the proven electromechanical core.
After going through a simpler prototype with dual-active suspension and with more robust sprockets, we identified that this system was unnecessary and difficult to assemble, so we maintained robustness while simplifying the assembly with a differential bar mechanism.
Powered entirely by URC-tested components, the shoulder joint is a custom-built 195-to-1 stepper motor and a 1.5-to-1 aluminum PETG laminated gear. The elbow and wrist joint use an EVA 17 stepper motor with a 50-to-1 reduction aided by a gear, and the gripper has been redesigned as a 4-bar linkage with a 2-to-1 reduction, using a 30-kilogram servo. The movement of the gripper now allows a better entry angle to grab objects, and fast swappable 3D-printed TPU and effectors allow rapid prototyping for compliant grip interfaces. The current prototype validates our philosophy, allowing us to precisely manipulate objects, carry heavy objects, and operate panel tasks with precision and fluidity.
To complement the precise feedback of our first degree of freedom powered by an ODrive S1, we're implementing a feedback loop for the 3 remaining stages using stepper motors with industrial drivers and an MPU 6050 encoder with 0.1 resolution, ensuring precise control and early fall detection. The new design also allows the system to be swapped or removed in under 10 minutes for faster configuration and easy access to the electronics.
Chipiro uses a remounted modular power architecture with 6S 5.5 ampere-hour LiPo packs and a centralized distribution board separating logic, actuators, and high-current drivetrain lines, plus an emergency stop for full shutdown of the system. For this iteration, we tested a dual parallel sliding battery system for increased capacity and hot swapping, validating load behavior and integration. Since weight optimizations met endurance targets, the dual pack was on hold, while development continues with planned cell-level voltage monitoring for improved autonomy and power management.
Running a ROS2 policy subscriber architecture on Jetson or Nano, we leverage ROS2 control for seamless team-to-real hardware deployment, routing commands to all drives and steppers via Teensy Bridge. We implemented custom inverse kinematics for point-in-space arm manipulation, shift to a more efficient single-driver setup, and develop a centralized base station video server to drastically reduce antenna bandwidth usage.
Our communication system operates on the 2.4 GHz band using an Ubiquiti bullet AC radio to deliver high throw output and long-range connectivity. The rover integrates a 15 decibels omnidirectional antenna for stable coverage during dynamic motion, while a 120 degrees sector antenna at the ground station increases directional gain and link reliability. Field tests consistently validated robust performance at distance approaching 1 kilometer.
To accelerate control and navigation testing, we adopt a simulation-first workflow utilizing RVS2 and Gazebo Fortress. Our omnidirectional drivetrain features a custom nav-to-bridge tail rod for holomonic vehicles, natively supporting Ackerman, pivot turn, and a cropped steering mode. Based on past URC experience, we deprecate LiDAR in favor of a robust sensor fusion approach, relying on an Intel RealSense D435i depth camera and an IMU, while actively developing a custom differential GPS system targeting 10mm RTK precision. For object detection, we utilize OpenCV package for markers and a YOLO architecture for water bottles and geological hammers. Furthermore, we are integrating a combined convolutional model optimized specifically to exploit the topological features of the Mars dry terrain.
Our onboard lab includes chemical and habitability tests based on our experience of URC 2025, which showed us the importance of this analysis to evaluate soil properties and potential biological activity. We use bentonite and anhydrine for chemical detection and assess habitability through nitrogen, phosphorus, potassium, and pH levels. All measurements are analyzed with a spectrometer, which also enables mineral analysis by detecting spectral peaks with the source irradiated with RGB light. In the field, a team-built drill collects a 15-gram sample while measuring humidity and temperature. 5 grams are sealed for the judges, and the rest is processed inside the rover using peristaltic pumps. Following modular architecture guidelines, we designed dedicated soil extraction module since the arm proved too complex for sampling.